You have already died today, not metaphorically, not spiritually. According to one of the most respected interpretations of quantum mechanics, there are branches of reality where your morning commute ended differently, where the cosmic ray hit the wrong molecule. Where the other driver looked at their phone 1 second earlier, you are not in those branches. You cannot be, because you are here, listening, alive, and the reason you are alive might not be luck. It might be physics. This is the story of quantum immortality, the man who invented it, and the price his family paid for believing it was real. But before we begin, if you enjoy these nighttime journeys, remember to like and subscribe. It helps us bringing you more videos like this. Now, let us begin. Tonight, we are going somewhere most people never come back from. We are going to the place where physics meets death, where the mathematics of the universe might guarantee that you, personally, can never stop existing. We will meet a physicist who believed his own theory so deeply that he asked his wife to throw his ashes in the garbage because he was certain he would wake up alive in another universe. His daughter believed it too. She took her own life and left a note saying she wanted to join her father in a parallel world. We will walk through the strangest thought experiment ever devised, one that involves a gun, a quantum particle, and a question that can only be answered by the person pulling the trigger. We will confront a version of immortality that is not a gift but a prison. And we will look at the mathematics that suggests, right now, in this moment, there are more versions of you than there are atoms in the observable universe. This is the story of quantum immortality, the many worlds interpretation, and the man who changed the way we understand reality and then drank himself to death at 51. Chapter 1. You have already died today. Think about this morning. You woke up, you got out of bed, maybe you made coffee, checked your phone, stepped outside. Routine, ordinary, nothing happened. But here is what you did not notice. At some point during the night, a cosmic ray, a subatomic particle traveling near the speed of light, passed through your body. It does this every single second. About 10,000 muons, the remnants of cosmic ray collisions in the upper atmosphere, pass through every square meter of the Earth's surface every minute. They pass through your skull, through your heart, through the delicate chemistry of your brain. Most of the time, nothing happens. The particle passes clean through. But occasionally, very occasionally, a cosmic ray strikes a molecule of DNA in just the wrong way. It triggers a mutation. A cell begins to divide incorrectly. A cascade begins. You did not notice. You never do. Now think about the drive, the commute. You approached an intersection. Another car was coming from the left. The timing worked out. You passed through safely. But what if the other driver had looked at their phone 1 second earlier? What if your tire pressure had been slightly lower, your reaction time slightly slower? There is a version of this morning where none of these tiny variables aligned. We do not think about this. We are not built to think about this. The human brain is a survival machine optimized for the present moment, not for calculating the astronomically thin margins by which we continue to exist. But the margins are real. They are always there. And quantum mechanics has something very unsettling to say about them. Before we get to the physics, consider the people who should not be alive. Roy Cleveland Sullivan was a park ranger in Shenandoah National Park in Virginia. Between 1942 and 1977, he was struck by lightning 7 times. 7. Not near misses, not electrical surges. Direct lightning strikes to his body. The first strike hit a fire lookout tower in 1942. Sullivan ran from the burning structure and a bolt hit his right leg, burning off his toenail. The second came in 1969 while he was driving his truck. Lightning hit the vehicle, traveled through the frame, and burned his eyebrows. The third, in 1970, caught him in his own front yard. The fourth, set his hair on fire. The 5th, 6th, and 7th followed in successive years, each one finding him like a heat-seeking missile locked onto a single human body. The odds of being struck by lightning once in a given year in the United States are roughly 1 in 1 million. The odds of being struck 7 times over a 35-year span are so low that mathematicians struggle to express the number meaningfully. It is not just unlikely. It crosses into a category that probability theory has trouble processing. Sullivan survived all 7 strikes. He died in 1983 at the age of 71, not from lightning, from a gunshot wound. The Guinness World Record still lists him as the person struck by lightning more times than any other human being on record. Now consider Juliane Koepke. On Christmas Eve, 1971, she boarded Lancer Flight 508 in Lima, Peru, with her mother. The Lockheed Electra turboprop climbed into a thunderstorm over the Amazon rainforest. Turbulence tore the aircraft apart at roughly 10,000 feet. Passengers, seats, luggage, sections of fuselage, all of it fell into the canopy below. 91 people were on that plane. 90 died. Juliane Koepke survived. She fell 2 miles, still strapped to her row of seats, spinning through open air, crashing through the jungle canopy, and landing in the dense undergrowth of the Peruvian Amazon. She had a broken collarbone, a gash on her arm, and a swollen eye. She was 17 years old. For 11 days, she walked through the rainforest. She followed a stream, the way her father, a zoologist, had taught her. She passed the bodies of other passengers. Insects burrowed into her wounds. She had no food. On the 11th day, she found a boat and a shelter belonging to local loggers. They found her hours later and carried her to safety. How did she survive the fall? Physicists and aviation experts have studied the case for decades. The best explanation involves a combination of factors so specific and so unlikely that replicating them deliberately would be nearly impossible. The row of seats acted as a crude airfoil. The dense jungle canopy absorbed impact energy across multiple layers. Wind conditions, body position, even the angle at which she hit the trees, all of it conspired in a sequence so narrow that the probability collapses into a number too small to feel real. And yet she lived. One more. Vesna Vulovic, a flight attendant for JAT Yugoslav Airlines, was aboard Flight 367 on January 26, 1972. At 33,330 feet, roughly the cruising altitude of a commercial airliner, the aircraft broke apart. An explosion, likely caused by a briefcase bomb in the cargo hold, tore the plane into 3 sections over Czechoslovakia. Every other person on the aircraft died. 27 passengers and crew. Vulovic fell more than 6 miles without a parachute. She landed in a section of fuselage that struck a snow-covered hillside at a steep angle. A former World War II medic found her screaming in the wreckage and administered first aid. She had a fractured skull, 2 broken legs, 3 broken vertebrae, and was paralyzed from the waist down. She was in a coma for 27 days. She spent 16 months in the hospital, and then she recovered. She walked again. She lived until 2016, dying at the age of 66. The Guinness World Records lists her fall as the highest survived without a parachute. Sullivan, Koepke, Vulovic. 3 people. 3 events so statistically improbable that conventional probability can barely account for them. Now here is the question that changes everything. What if these are not miracles? What if these are not anomalies or freak accidents or lucky breaks? What if there is a mechanism buried in the deepest layer of physical law that makes this kind of survival not just possible but, from a certain perspective, inevitable? This is where quantum mechanics enters the room, and the room gets very strange. In 1957, A 26-year-old doctoral student at Princeton University named Hugh Everett III submitted a thesis that proposed something radical. He argued that the wave function, the mathematical description of a quantum system, never collapses. It never reduces to a single outcome. Instead, every possible outcome of every quantum event actually occurs. The universe does not choose one path, it takes all of them. This means that when a photon hits a beam splitter and has a 50-50 chance of going left or right, both things happen. The universe splits. In one branch, the photon went left. In the other, it went right. Both branches are equally real. Both continue forward. And every particle, every interaction, every quantum event in the entire cosmos does this constantly. Everett called this the relative state formulation. Physicist Bryce DeWitt later gave it the name we know today, the many worlds interpretation of quantum mechanics. If this interpretation is correct, the consequences are staggering. Not billions of parallel universes, not trillions. An uncountable infinity of them, branching at every quantum interaction, stretching backward to the origin of time itself. Every version of events that quantum mechanics permits is real somewhere. Every roll of the dice lands on every number. And here is where it gets personal. If every possible outcome of every quantum event is realized, then there exist branches of the universal wave function where you survived everything. Every close call, every near miss, every disease that could have taken you, every accident that almost did. In most branches, the cosmic ray hits your DNA and nothing happens. In a vanishingly small number, it triggers something. But you, the conscious observer, can only ever find yourself in a branch where you survived. You cannot experience your own death, because experience requires a living observer. This is not mysticism. This is not wishful thinking. This is a direct, logical consequence of one of the most mathematically rigorous interpretations of quantum physics ever proposed. And in 1998, physicist Max Tegmark at the Massachusetts Institute of Technology formalized this implication into a thought experiment so disturbing that many physicists refused to discuss it publicly. He called it quantum suicide. The setup is simple. Imagine a gun connected to a quantum random number generator. The generator measures the spin of a subatomic particle. Spin up, the gun does not fire. Spin down, the gun fires. 50-50 odds, pure quantum randomness, no hidden variables, no way to predict the outcome. You sit in front of the gun. The trigger is pulled. Under the Copenhagen interpretation of quantum mechanics, the standard view taught in most physics classrooms, what happens is simple. There is a 50% chance you live and a 50% chance you die. Pull the trigger 10 times, and the odds of surviving every single round are roughly 1 in 1,024. The math is clean, cold, and final. But under the many worlds interpretation, something else happens entirely. Each time the trigger is pulled, the universe branches. In one branch, the particle is spin up and the gun does not fire. In the other, the particle is spin down and it does. Both branches are real. But you, the person sitting in the chair, can only ever experience the branch where you survived. The branch where you died is real, but you are not in it. Your consciousness continues only along the path where the gun clicked. Pull the trigger again. Same result. The universe splits again. Again, you survive. Again, the other branch carries a version of the experiment where you did not. Pull the trigger 100 times, 1,000 times, 1,000,000 times. From the outside, your friends see a dead body after the first or second pull. But from the inside, from your first-person perspective, the gun never fires. It clicks every single time. And this is not luck. This is physics. This is what the mathematics predicts if you take the many worlds interpretation seriously and follow its logic to the end. Tegmark himself pointed out something crucial. This experiment can only convince one person, the person sitting in the chair. Everyone else sees the expected statistics. Everyone else sees death. Only you experience the impossible string of survivals. Only you get the evidence, and you can never share it. This is quantum immortality, the idea that from your own subjective viewpoint, you can never die, not because death does not happen, but because you can never be present to experience it. Every quantum branching event that could end your life simply routes your consciousness to the branch where it does not. Think about that for a moment. Think about Roy Sullivan and his 7 lightning strikes. Think about Julian Kepka falling 2 miles through the atmosphere and walking away. Think about Vesna Vulovic dropping 6 miles without a parachute and living to 66. What if they are not extraordinary? What if they are simply people who happen to have had their survival made visible? What if every single person alive right now has already survived an uncountable number of events that, in other branches, ended their life? What if you are the version of yourself that has beaten impossible odds over and over and over again, and you do not know it because you were never in the branches where you lost? That question is where this journey begins. And the man who first asked it, who first wrote the mathematics that made it possible, paid a price for the answer that few people know about. His name was Hugh Everett III, and his story is one of the strangest, saddest, and most consequential in the history of modern physics. Chapter 2: The Deadliest Experiment Ever Proposed. Let us go back to the gun. Not a metaphorical gun, not a philosophical exercise dressed up in polite language. A real mechanism, built to do one thing: end a life based on the spin of a single subatomic particle. Max Tegmark, then at Princeton University and later a professor of physics at the Massachusetts Institute of Technology, laid out the quantum suicide thought experiment in a paper published in 1998. He did not invent the core idea. That belonged to Hugh Everett III, who privately discussed versions of it as early as the late 1950s. Independent formulations were published by Hans Moravec in 1987, Bruno Marchal in 1988, and Hugh Price in 1997. But Tegmark gave it a name, a structure, and a rigor that forced the physics community to confront what it actually implied. The experiment works like this. You build a device. At its core is a quantum random number generator. This generator measures a quantum property, typically the spin of a particle. In quantum mechanics, spin is a fundamental property of subatomic particles. When measured along a chosen axis, the result is binary: spin up or spin down. The outcome is genuinely random, not pseudo-random, not chaotic but deterministic underneath. Quantum random. No hidden variables determine the result in advance. No information anywhere in the universe can predict whether the next measurement will be up or down. The generator is connected to a device capable of ending the experimenter's life instantly. In Tegmark's description, it is a machine gun. If the spin is measured as down, the weapon fires. If the spin is measured as up, it makes an audible click, and nothing happens. The experimenter sits in front of the device. A sandbag is placed in front of the weapon first, as a test. An assistant pulls the trigger 10 times. The experimenter hears a random sequence: click, bang, bang, click, bang, click, click, bang, bang, click. Roughly half fire and half do not. The device works. Both outcomes occur with the expected frequency. Now the sandbag is removed. The experimenter sits in the line of fire. The assistant leaves the room. The experimenter reaches for the trigger. And here is where the two great interpretations of quantum mechanics diverge completely. Under the Copenhagen interpretation, the story is straightforward. The wave function describes probabilities. When the measurement is made, the wave function collapses to one outcome: Spin up or spin down, 50-50. If the result is spin down, the weapon fires and the experimenter dies. Full stop. There is no continuation. Consciousness ends. The experiment is over. Run the experiment 10 times, and the odds of surviving every round are approximately 1 in 1,024, less than 1/10 of 1%. Run it 20 times, and the probability drops below 1 in a million. Run it 100 times, and the number of zeros after the decimal point stretches longer than a phone book. The Copenhagen interpretation says that the experimenter dies quickly, predictably, with all the certainty that half a century of experimental physics can muster. Under the many worlds interpretation, something radically different happens. When the trigger is pulled, the universe does not collapse to one outcome. It branches. In one branch, the spin is up, the gun clicks, and the experimenter lives. In the other branch, the spin is down, the gun fires, and the experimenter dies. Both branches are real. Both continue. Neither is a ghost or a shadow of the other. But consciousness is a peculiar thing. You cannot be conscious in a branch where you are dead. Consciousness requires a functioning brain. A functioning brain requires being alive. So your subjective experience, the unbroken thread of awareness that you call yourself, can only continue in the branch where the gun did not fire. The trigger is pulled again. The universe branches again. Again, you survive. The other branch is real. And in it, you are dead, and your friends are mourning, and the experiment is reported as a failure. But from your perspective, the gun clicked again. This is the core horror of the quantum suicide thought experiment. From the outside, you die quickly and predictably. From the inside, you never die at all. And the distinction between inside and outside is absolute. No communication crosses the boundary. No signal travels between branches. The friend who watched you die in their branch cannot send a message to the version of you that survived in yours. The branches are real but isolated, like rooms in a house with no doors between them. Tegmark identified 3 criteria that a true quantum suicide experiment must satisfy. First, the random number generator must be genuinely quantum, not a coin flip, not a computer algorithm, a quantum measurement with outcomes determined by the superposition of states. If the randomness is classical, no branching occurs. The experiment proves nothing. Second, the killing mechanism must act faster than the experimenter can become aware of the outcome. Death must be instantaneous. If there is a delay between the measurement and the lethal action, even a fraction of a second, the logic breaks down. The experimenter might experience a moment of knowing the result before dying, which complicates the branching structure in ways that undermine the argument. Third, the mechanism must be certain to kill the experimenter, not injure, not knock unconscious, not leave a chance of survival through medical intervention. The experiment requires a clean binary, alive or dead. No middle ground. These criteria are important because they are what separates quantum suicide from ordinary near-death experiences. A car crash is not a quantum suicide experiment. The randomness is classical. The outcome is not binary. Consciousness fades gradually. There are 1,000 intermediate states between alive and dead, and the many worlds interpretation has specific things to say about each of them. And this is where things become deeply uncomfortable. Because quantum suicide, as Tegmark described it, is the only experiment that could distinguish between the Copenhagen interpretation and the many worlds interpretation from the first-person perspective. Every other experiment gives the same results under both interpretations. Both predict the same probabilities for the outcomes of any measurement. Both match the experimental data. Both pass every test. The debate between them has raged for decades precisely because there seems to be no empirical way to settle it. Quantum suicide changes that. If you survive 100 rounds, 1,000 rounds, 10,000 rounds, The Copenhagen interpretation says the probability of that happening is so low that it effectively cannot occur. But under the many worlds interpretation, it is guaranteed. You must survive. The version of you that can observe anything at all must be the version that lived. So if you sit in the chair, pull the trigger 10,000 times, and find yourself alive, you have evidence for many worlds that no other experiment can provide. But here is the catch. You can never share that evidence with anyone. Your friends, your colleagues, the scientific community, they exist in branches where you died. To them, you pulled the trigger and the gun fired, and the experiment ended badly and quickly. They will never see your impossible survival. They will never receive your triumphant paper explaining the results. They will attend your funeral and file the experiment under failure. Only you know. Only you have the evidence, and you can never transmit it across the branch boundary. It is the perfect experiment and the most useless one simultaneously. Perfectly informative for one observer, completely invisible to everyone else. Physicist David Deutsch, one of the most prominent advocates of the many worlds interpretation and a pioneer in quantum computing, has been cautious about quantum suicide. He has argued that the standard way of applying probabilities does not directly support the quantum immortality conclusion. It requires an additional assumption, namely that when making decisions, one should ignore the histories in which the decision maker is absent. Deutsch has said that his guess is that this assumption is false. Sean Carroll, a physicist at Johns Hopkins University and another supporter of many worlds, has taken a similar position. Carroll argues that future versions of yourself that result from quantum branching should be considered distinct persons. Killing some of them to benefit others is not rational. It is not different from ordinary harm. The fact that some versions survive does not make the experiment acceptable any more than the fact that other people will survive your death makes dying acceptable. And Tegmark himself, the man who formalized the experiment, has stepped back from the strongest version of quantum immortality. He now argues that the experimenter should only expect a normal probability of survival, not guaranteed immortality. His reasoning involves branch weights. After the gun fires in some branches and does not fire in others, the surviving version of the experimenter exists with a much lower measure in the overall wave function. A lower measure means you are less likely to find yourself in that state. The anthropic principle, he argues, suggests that you should expect to find yourself where your existence is most probable, not where it is least. In other words, even the architects of the thought experiment are not sure it works. And yet, the logic has never been formally refuted. No one has produced a mathematical proof that quantum immortality is impossible under many worlds. The interpretive debate continues. The thought experiment sits at the center of quantum foundations like a loaded weapon that nobody wants to touch, but nobody can put away. Here is what makes it so disturbing. People have taken it seriously, not just as philosophy, as a real possibility. In online forums dedicated to quantum mechanics and the many worlds interpretation, people have discussed attempting quantum suicide experiments. Some have described carrying weapons to casinos to test their luck against quantum odds. Some have seen the logic as a reason to take extreme risks, reasoning that if they die, they will simply not experience the outcome, and if many worlds is correct, they will always find themselves in the surviving branch. This is exactly why many physicists refuse to discuss quantum suicide publicly. Not because the logic is wrong, but because the logic, followed to its extreme, encourages a kind of reasoning that is incompatible with how we actually live and value life. Jacques Mahler, a physicist who has written extensively on this topic, has called quantum immortality a potentially life-threatening delusion. He argues that the reasoning contains a subtle but critical error in how it handles personal identity across branches. Your continued existence in one branch does not benefit the version of you that ceases to exist in another. The branches are separate. The selves are separate. Survival in one place is not survival everywhere. This is important. This is the line where physics becomes personal. Because quantum suicide is not just a thought experiment about interpretation, it is a thought experiment about you, about what it means to be you, about whether the thing you call yourself is a single thread or a branching tree, and whether the survival of one branch compensates for the death of another. And the man who started all of this, who wrote the equations that made the question possible, believed in his answer completely. Hugh Everett III, according to his biographer, Eugene Shikovtsev, firmly believed that his many worlds theory guaranteed him immortality. He argued that his consciousness was bound at each branching to follow whatever path did not lead to death. He did not just think it was an interesting theoretical possibility. He believed it the way other people believe in gravity. He believed it so deeply that he asked his wife to throw his ashes in the trash. Why preserve the remains of a body if the consciousness has simply moved on to another branch? And when his daughter Elizabeth took her own life 14 years later, she left a note saying she wanted her ashes thrown in the trash too, so she could end up in the correct parallel universe to meet up with her father. That note is one of the most haunting documents in the history of physics. A daughter suffering from severe mental illness, using the mathematical framework of quantum mechanics to rationalize the end of her life, a framework her father built, a framework that told her, in the language of wave functions and probability amplitudes, that death was not an ending, but a doorway. The experiment you cannot cheat. The theory you cannot escape. The question you can only answer for yourself. And it begins not with guns or particles or wave functions. It begins with a much darker question. What happens if quantum immortality is real and you cannot opt out? What happens when immortality is not a reward but a sentence? Chapter 3. The Curse of Living Forever. Every culture in human history has dreamed of immortality. The Epic of Gilgamesh, written roughly 4,000 years ago in ancient Mesopotamia, is a story about a king who watches his closest friend die and then crosses the world to find the secret of eternal life. The ancient Egyptians built entire civilizations around the preservation of the body after death. The Chinese alchemists spent centuries searching for the elixir of life. Ponce de Leon allegedly crossed the Atlantic, seeking the fountain of youth. Silicon Valley executives today pour billions into longevity research, caloric restriction, blood transfusions, and cryonics, all chasing the same ancient dream. The assumption is always the same. Immortality is desirable. Death is the enemy. To live forever is the ultimate victory. Quantum immortality flips this assumption on its head. Because if the many worlds interpretation is correct, and if the logic of quantum suicide holds, then immortality is not something you achieve. It is something you cannot escape. And that changes everything. Let us follow the logic. You are alive right now. You are listening to this. In the many worlds interpretation, at every quantum branching event that could have ended your life, you continued along the branch where it did not. This has been happening since the moment you were conceived, since the first cell divided, since the first chemical bond formed in the right configuration to build you. You have been surviving quantum events for your entire life without knowing it. Now extend this forward. You age. Your cells accumulate damage. Your telomeres shorten. Your organs slowly degrade. You develop the conditions that eventually accompany old age. Heart disease, cancer, neurodegeneration. The body fails. It is failing right now. In fact, one cell at a time, held in check by repair mechanisms that themselves degrade over decades. Under normal probability, this process ends. The body fails beyond the capacity of its repair systems. You die. The conscious experience, that is you, terminates. This is what happens in the vast majority of branches. But in a vanishingly tiny fraction of branches, something else happens. The cancer does not develop. The arterial plaque does not rupture. The aneurysm does not burst. The fall does not break the hip. The infection does not take hold. Every single event that could have ended your life at every single moment goes the other way. Not because of magic, because quantum events underpin everything, including the molecular interactions inside your body, and in some branches, the outcomes all happen to align in favor of your continued survival. The probability of this is astronomically low, lower than any number that has practical meaning. But if every branch is real, if every possible quantum outcome is realized somewhere, then there exists a branch where you survive. And if consciousness can only experience the branch where it continues, then you find yourself there, always. Here is the nightmare. You are 90 years old. Your body is failing. In nearly every branch, you have already died. Your friends are dead. Your family is dead. The world has moved on. But in one thin branch, one impossibly narrow thread of the universal wave function, you are still alive. Not well, not comfortable, just alive. Your mind is deteriorating. Memories are slipping. You cannot always remember the names of people you loved. Your body is in pain. Constant, grinding, low-level pain that medication cannot fully touch. You cannot move without assistance. You cannot eat without assistance. Your world has contracted to a single room, a single bed, a single window looking out on a world you barely recognize. And you do not die. The heart keeps beating, not strongly, not well, but enough. The lungs keep drawing air, the brain keeps firing, though with diminishing coherence. Every quantum event that could have released you from this went the other way. In this branch, you survive. In this branch, you always survive. 100 years old. 110, 120. The Guinness World Record for the oldest verified human is Jean Calment of France, who lived to 122 years and 164 days, dying in 1997. But the many worlds interpretation does not care about records. It does not care about what is typical. It only cares about what is possible. And as long as there exists some quantum configuration that keeps you alive, even barely, even miserably, you continue. 200 years old. The branch is so thin now, so improbable, that trillions upon trillions of other branches have long since seen your death. But this one persists. Your body is held together by machines, by interventions, by an unbroken chain of quantum coincidences that defies comprehension. And you are aware, partially, dimly, aware enough to know that you exist, aware enough to suffer. This is the dark side of quantum immortality that most popular explanations skip over. It is not a promise of eternal youth. It is not resurrection. It is not heaven. It is the guarantee that your subjective experience never reaches zero. You asymptotically approach death without ever arriving. You get closer and closer to nothing while never quite getting there. The philosopher Friedrich Nietzsche proposed the concept of eternal return, the idea that everything that has happened will happen again, identically, infinitely. He called it the heaviest burden, the most terrifying thought a human being could confront. Quantum immortality is worse. In eternal return, you repeat the same life. The joys come back along with the suffering. In quantum immortality, the joys thin out. The branches where good things happen become rarer and rarer as your body degrades. What remains is persistence without purpose, existence without experience, and there is no exit. This is the cruelest implication of the thought experiment. Even deliberate attempts to end one's life would, under strict quantum immortality, fail from the first-person perspective. The gun jams. The fall is broken. The dosage is insufficient. In every branch where you survive, no matter how desperately you might want to stop. Tegmark himself addressed this directly. He pointed out that the flaw in extending quantum suicide to ordinary real-world dying is that death is not usually a binary event. It is a process, a gradual fading, a continuum of states between fully conscious and fully dead. The quantum suicide thought experiment works because it manufactures an artificial binary, alive or dead. No middle ground. But real dying is messy. It takes time. Consciousness dims gradually, like a light on a slow dimmer. In Tegmark's words, although you cannot experience a timeline where you are altogether absent, you can enter one in which your speed of thought is diminishing, your memories and other faculties fading. He said he was confident that even if a person cannot die all at once, they can gently fade away. This is important. It means that even within the many worlds framework, strict quantum immortality, the version where you survive To understand the man, you have to go back to a lonely childhood in Washington, D.C., a letter to Albert Einstein, and a night at Princeton University where a bottle of sherry changed the history of physics. Chapter 4. The Man the Universe Forgot. Hugh Everett III was born on November 11, 1930, in Washington, District of Columbia. It was not a warm beginning. His parents separated when he was young. His mother, Catherine Lucille Kennedy, raised him for his first 7 years. Then his father, Hugh Everett Jr., a military officer, took over along with his stepmother, Sarah Thrift. The boy was quiet, bookish, intensely mathematical, in a way that set him apart from other children. He did not make friends easily. He did not share easily. What he had, from a very early age, was a mind that moved in straight lines through complicated problems, cutting through ambiguity with a kind of cold precision that could be mistaken for arrogance, but was really just efficiency. At 12 years old, Hugh Everett III did something remarkable. He wrote a letter to Albert Einstein. The letter asked a question about the nature of the universe. What holds it together? Is there something random at the core, or something unifying? The question itself is less important than the fact that a 12-year-old boy had the audacity to write it and the intellectual framework to articulate it. Einstein responded. His reply was brief and characteristically warm. He wrote, "There is no such thing as an irresistible force and an immovable body, but there seems to be a very stubborn boy who has forced his way victoriously through strange difficulties created by himself for this purpose." That letter sits in the archives today, a small piece of paper connecting two of the most important minds in the history of physics, one at the end of his career, the other at the very beginning. Everett won a half scholarship to St. John's College High School in Washington, D.C. From there, he moved to the Catholic University of America, where he studied chemical engineering as an undergraduate. He was brilliant. He was also, according to classmates, a committed atheist at a Catholic institution, a combination that generated friction. According to his biographer, Peter Byrne, Everett drove devout Jesuits to distraction with scientific questioning and once presented a logical proof against the existence of God that reportedly caused one of his professors to lose his faith. At Catholic University, Everett encountered something that would quietly shape the rest of his life. He read about Dianetics in astounding science fiction magazine. Dianetics, the precursor to Scientology, proposed that the mind could be understood as a kind of computing machine and that conventional medicine was fundamentally flawed. Everett never became a Scientologist, but he retained a deep distrust of conventional medicine for the rest of his life. He would never voluntarily see a doctor, never submit to a physical examination, never seek treatment for the conditions that were slowly destroying his body. This detail matters. It matters enormously. He graduated in 1953 and moved to Princeton University on a National Science Foundation fellowship. Princeton in the 1950s was the center of the physics universe. Albert Einstein was still alive, still working at the Institute for Advanced Study just down the road. John Archibald Wheeler, one of the most creative theoretical physicists in the world, was on the faculty. Wheeler had helped develop the theory of nuclear fission alongside Niels Bohr. He had worked on the Manhattan Project. He had coined the term black hole. His list of graduate students reads like a who's who of 20th century physics. Richard Feynman, Jacob Bekenstein, Kip Thorne, and now Hugh Everett III. Everett took classes in mathematical physics with Eugene Wigner, the Hungarian physicist who would later win the Nobel Prize. Wigner had his own views on quantum mechanics. He argued that human consciousness, perhaps even some form of cosmic consciousness, was essential for the collapse of the wave function. The act of observation, Wigner believed, was not just a physical process. It involved the mind in a fundamental way. Everett found this deeply unsatisfying, not because it was mystical, though it was, but because it was arbitrary. Why should consciousness be special? Why should the human mind occupy a privileged position in the mathematics of the universe? The equations of quantum mechanics did not require it. The equations described superposition and evolution and probability. The collapse was added by hand, imposed on the mathematics from outside, like a rule in a game that no one could explain. Everett began to wonder, what if the collapse was not real? What if the wave function never collapses? What if the mathematics, taken at face value, was telling the complete truth? The moment of insight came on a night in 1954. Everett was at a gathering with his fellow graduate student Charles Misner and a visitor named R.G. Peterson, who was an assistant to Niels Bohr. They were drinking sherry. They were talking about physics. And specifically, they were thinking up what Everett later described as ridiculous things about the implications of quantum mechanics. What if the wave function is everything? What if there is no collapse? What if the observer is not outside the system but inside it, described by the same mathematics as everything else? The idea hit him like a wave. Not a gradual realization, a sudden insight. The mathematics was already there. Erwin Schrödinger had written the equation. Paul Dirac had developed the formalism. John von Neumann had proved that quantum mechanics was mathematically complete. All of the tools existed. What Everett did was something simpler and far more radical. He took the existing mathematics seriously. He proposed that the wave function of the universe, the total quantum state of everything that exists, never collapses. It evolves according to the Schrödinger equation at all times, without exception, without interruption, without magical intervention by observers or measuring devices or conscious minds. When a measurement is made, what appears to happen, the apparent collapse to a single outcome, is explained by the observer becoming entangled with the system being measured. The observer does not see one result because the other results cease to exist. The observer sees one result because the observer has split. In one branch of the wave function, the observer sees spin up. In another branch, the observer sees spin down. Both branches are real. Both observers are real. Neither knows about the other. This was the relative state formulation of quantum mechanics. The idea that the state of any system is defined only relative to the state of the observer who measures it. There is no absolute outcome. There is no universal perspective from which one result is real and the other is not. There are only relative states, correlated through entanglement, branching endlessly as the universe evolves. Everett spent the next year and a half developing this idea into a doctoral thesis. The first draft, written in 1956, was 137 pages long. It was dense, mathematical, and uncompromising. Everett called it the theory of the universal wave function. He laid out the mathematics with care. He showed that his formulation was consistent with all experimental observations. He demonstrated that the appearance of probability, of randomness, of wave function collapse could be derived from the mathematics of a wave function that never collapsed, simply by considering how observers within the system would experience their own correlations with the objects they measured. Wheeler was excited. He recognized the brilliance of the approach. He also recognized the danger. Because Everett's thesis was not just a new interpretation, it was a direct challenge to the most powerful physicist alive, Niels Bohr, the architect of the Copenhagen interpretation, the man who had beaten Einstein in public debate, the man whose word, in the physics community of the 1950s, was something very close to law. Wheeler knew that if Everett's thesis was presented the wrong way, it would be dismissed, not refuted, dismissed, waved away, treated as the work of a crackpot, not a colleague. The physics establishment of the 1950s was not kind to heresies, and what Everett was proposing was the greatest heresy in quantum mechanics since Einstein told Bohr that God does not play dice. Wheeler began to work on Everett. He told him to revise the thesis, soften it, remove the most provocative language, cut the sections that directly challenged Bohr's complementarity principle, reduce the 137-page manuscript to something shorter, something more palatable, something that could pass the review process without detonating. Everett resisted. Wheeler insisted. The result was a compromise that satisfied no one. The thesis was cut from 137 pages to roughly 36. The title was changed from the theory of the universal wave function to the more modest relative state formulation of quantum mechanics. The most radical implications, the ones about multiple worlds, multiple observers, multiple copies of everything, were softened or buried beneath careful phrasing. Wheeler wrote a companion paper to accompany Everett's thesis, designed to make the work digestible for skeptical readers. He knew Everett's committee would struggle with the material. He wanted a diplomatic bridge. The oral examination took place on April 23, 1957. The committee included Wheeler, Valentine Bargmann, H. W. Wild, and Robert Dick. They concluded that the candidate passed a very good examination. He dealt with a very difficult subject and defended his conclusions firmly, clearly, and logically. He shows marked mathematical ability, keenness in logic analyses, and a high ability to express himself well. Everett had his doctorate, but the real test was not the committee. The real test was Bohr, and that test was about to begin. Chapter 5. The War with Bohr. To understand what happened to Hugh Everett's theory, you have to understand the empire it challenged. Niels Henrik David Bohr was born in Copenhagen, Denmark, in 1885. By the time Everett submitted his thesis in 1957, Bohr was 71 years old and had spent half a century at the absolute center of theoretical physics. He had won the Nobel Prize in Physics in 1922 for his model of the atom. He had founded the Institute for Theoretical Physics in Copenhagen, which became the intellectual headquarters of quantum mechanics. He had mentored an entire generation of physicists: Werner Heisenberg, Wolfgang Pauli, Max Born, Lev Landau, among them. He had debated Einstein at the Solvay conferences and, in the judgment of most of the physics community, won. Bohr did not merely contribute to quantum mechanics. He defined how it was understood. The Copenhagen interpretation, the framework that Bohr and Heisenberg developed in the late 1920s, was not just one interpretation among many. It was the interpretation. For 3 decades, it had dominated physics education, physics research, and physics culture. Students learned it in their first quantum mechanics courses. Textbooks presented it as established fact. Dissenting views were not refuted so much as ignored. The phrase that captured the spirit of the era was coined by physicist David Mermin: "Shut up and calculate. Do not ask what the wave function means." He said it casually, as if it did not matter, but people who knew him said it mattered deeply. The rejection burned. It settled into him like a coal. At the Pentagon, Everett found work that used his mathematical abilities in a completely different arena. He calculated death. His assignment was to model the effects of nuclear war. How many people would die in a first strike? How would radioactive fallout disperse across continents? What were the mortality rates for different targeting strategies? How many hydrogen bombs would be needed to destroy the Soviet Union's capacity to retaliate? This was not abstract work. Everett's calculations directly informed policy decisions during the most dangerous period of the Cold War. He briefed officials in both the Eisenhower and Kennedy administrations. He helped develop targeting protocols for nuclear weapons. He worked on the Single Integrated Operational Plan, known as PSYOP, the master plan for nuclear war that would have launched American missiles at predetermined targets across the Soviet Union. The irony is almost unbearable. The man who had proposed that every possible outcome of every quantum event actually occurs, that death in one branch is accompanied by survival in another, that consciousness is immortal, spent his working days calculating how many millions of people would die in a nuclear exchange. The mathematician of infinite survival became the mathematician of mass death. He was good at it. His mathematical skills were exceptional, and the Pentagon valued precision. He rose through the ranks. He helped found Lambda Corporation in 1964, a defense analysis firm that applied military modeling techniques to civilian problems. Later, in 1973, he and a colleague founded DBS Corporation, a contracting firm that worked with various federal departments. But Everett never returned to physics. He never published another paper on quantum mechanics. He never attended another physics conference. He never responded to the few physicists who wrote to him asking about his thesis. He had been silenced, not by force but by indifference, and the silence was total. Meanwhile, the idea he had abandoned began, very slowly, to come alive. In 1967, Bryce DeWitt, a physicist at the University of North Carolina, developed what became known as the Wheeler-DeWitt equation, a theoretical framework for quantum gravity that required something very close to Everett's universal wave function. DeWitt credited Everett for demonstrating the need for such an approach. In 1970, DeWitt wrote an article for Physics Today in which he described Everett's relative state theory and gave it a new name. He called it the many worlds interpretation. The article drew letters from physicists. Debate stirred. In 1973, DeWitt and his graduate student Neil Graham published an anthology titled The Many Worlds Interpretation of Quantum Mechanics. The book featured the full, uncut, 137-page version of Everett's original thesis, the version Wheeler had insisted on gutting for the 1957 publication. The book sold out completely. The theory that the physics establishment had buried in 1957 was rising from the ground, but Everett, the man who had written it, was not there to see it. He was somewhere else, somewhere darker, somewhere that the many worlds interpretation, for all its mathematical elegance, could not reach. Chapter 6. Drinking himself out of the universe. By the late 1960s, Hugh Everett III had become a ghost in his own house. He lived in McLean, Virginia, a quiet suburb outside Washington, D.C., with his wife Nancy and their two children, Elizabeth and Mark. From the outside, the family looked comfortable. Everett earned well from his defense work. The house had an indoor swimming pool. He drove good cars. He ate at fine restaurants. He collected gadgets and carried a small microfilm camera on his belt wherever he went. From the inside, the house was a mausoleum. Everett smoked 3 packs of cigarettes a day. He drank heavily and steadily. Gin, whiskey, whatever was available, starting early and continuing through the evening. He ate without restraint, and his weight climbed year after year until he was grossly obese by any medical standard. He never exercised. He never went to a doctor. The distrust of conventional medicine he had picked up from reading about Dianetics at Catholic University had hardened into something more like a principle. He would not submit to examination. He would not take medication. He would not have blood drawn or blood pressure checked or lungs listened to. He simply refused. His colleagues at DBS Corporation, the defense contracting firm he co-founded, noticed the decline. They saw a man of extraordinary mathematical ability wrapped in a body that was deteriorating in real time. He was brilliant in meetings. He could solve problems that stumped entire teams, but he moved slowly, breathed heavily, smelled of tobacco, and radiated a kind of impenetrable distance that made personal connection impossible. At home, the distance was worse. Mark Oliver Everett, Hugh's son, would later become famous as the musician known simply as E, the lead singer and songwriter of the rock band Eels. But in the 1970s, Mark was a boy growing up in a house where his father existed as furniture. Mark has spoken about this in interviews, in his autobiography, and in a BBC documentary called Parallel Worlds, Parallel Lives. His descriptions are precise and devastating. His father sat at the dining room table, always at the table, smoking, drinking, thinking about something Mark could never access. He did not play with his children. He did not talk to them about their days, their interests, their problems. He did not attend school events. He did not offer affection. He was a presence without warmth, a body in a chair with a mind pointed somewhere else. Mark has said that the first time he and his father had any physical contact that he could remember was when Mark found his father's body. One night, near the end, Hugh came into the kitchen while Mark was doing the dishes. Mark was startled. His father almost never initiated conversation. Hugh looked at him and asked, incredulously, "You are doing the dishes?" Mark said yes. Hugh considered this for a moment and then left the room. That was the interaction. That was what passed for connection in the Everett household. Nancy Everett endured a marriage that had been deteriorating for decades. According to Peter Byrne's biography, the relationship was marked by mutual infidelity, emotional isolation, and growing resentment. Hugh was distant and self-absorbed. He reportedly had affairs and visited prostitutes. Nancy, in turn, sought connection elsewhere. They stayed together. They did not thrive together. Elizabeth, their daughter, struggled with mental illness from an early age. She was institutionalized multiple times. She underwent extensive electroconvulsive therapy, a treatment that was more common and more aggressive in its application during the 1970s and 80s than it is today. Her suffering was chronic, severe, and visible to everyone in the family. And through all of it, Hugh Everett sat at his table, smoking, drinking, saying nothing. There is a terrible irony here, and it is worth stating plainly. The man who proposed that consciousness is immortal, that the wave function guarantees survival, that death in one branch is accompanied by continuation in another, lived as though life had no particular value. He made no effort to preserve his own health. He watched his body break down with the detachment of a scientist observing an experiment that has already been decided. Biographer Eugene Shekhovsev wrote that Everett firmly believed his many worlds theory guaranteed him immortality. His consciousness, Everett argued, was bound at each branching to follow whatever path did not lead to death. If this is true, and the account suggests it is, then Everett's self-destruction begins to look less like carelessness and more like a logical conclusion. Why take care of a body that is going to be discarded anyway? Why extend the life of a vehicle when the passenger will simply transfer to another? If death is just a branching event that routes consciousness to the surviving path, then dying young is not a loss, it is a transition. Peter Byrne, who investigated Everett's life extensively and had access to unpublished papers discovered in Mark Everett's basement, pushed back against this reading. Byrne wrote that it is unlikely Everett subscribed fully to the quantum immortality view, since the only sure thing it guarantees is that the majority of your copies will die, hardly a rational goal. But the evidence of Everett's behavior suggests otherwise. He lived as though death was not a concern. He drank and smoked and ate with abandon. He refused medical care. He did not exercise. He showed no anxiety about his declining health. He seemed, to those who knew him, to regard his physical existence with something approaching contempt. Elaine Tsiang, a former employee at DBS Corporation, recalled that Hugh liked to espouse a form of extreme solipsism. She said that although he took pains to distance his many worlds theory from any theory of mind or consciousness, obviously they all owed their existence relative to the world he had brought into being. This is a strange and revealing statement. A man surrounded by colleagues who depended on him for their livelihoods, by a wife who shared his bed, by children who needed a father, regarding all of them as relative states in a wave function that centered on himself, not cruelty exactly, something colder. A mathematical solitude so complete that other people became variables in an equation, rather than beings with their own irreducible reality. And yet, there were moments. In 1977, 20 years after his thesis was published, Hugh Everett received an invitation he did not expect. John Archibald Wheeler, his former thesis advisor, had organized a quantum mechanics conference at the University of Texas at Austin. Wheeler wanted Everett to come, to talk about his theory, to rejoin, even briefly, the world he had left behind. Everett went. He took his family. He treated it as a vacation from his defense work, and for the first time in 2 decades, he stood before an audience of physicists and talked about the many worlds interpretation. The reception was extraordinary. The physicists in the room were not the same generation that had dismissed his work in the 50s. These were younger researchers, many of whom had read DeWitt's anthology and found the ideas compelling. Among the audience was David Deutsch, then a graduate student of Wheeler's, who would later become one of the foremost advocates of many worlds and a pioneer of quantum computing theory. Deutsch has said that meeting Everett at that dinner was a formative moment. Everett gave his talk. It was well received. People asked questions. People engaged with the mathematics. For a few hours, in a lecture hall in Texas, Hugh Everett III was a physicist again. He enjoyed it. By all accounts, he genuinely enjoyed it. He had never wavered in his belief in his theory. He had simply stopped talking about it. And now, 2 decades later, the world had begun to catch up. But nothing came of it. Wheeler tried to arrange a path back into physics for Everett. He proposed establishing a new research institute in California where Everett could work on quantum foundations. The proposal went nowhere. Everett returned to Virginia. He returned to DBS. He returned to the table, the cigarettes, the gin. Wheeler himself would later distance himself from many worlds. In 1980, he said he thought the theory creates too great a load of metaphysical baggage to carry along. The mentor who had encouraged the student had, in the end, joined the establishment that rejected him. On July 19, 1982, Hugh Everett III died in his sleep at his home in McLean, Virginia. He was 51 years old. The cause was a heart attack. Given his smoking, his drinking, his obesity, and his absolute refusal to see a doctor, the heart attack was not a surprise. It was a certainty postponed. The only question had ever been when. Mark Everett, then 19 years old, found the body. His mother and sister were away. Mark walked into the room and saw his father lying still. He touched him. He has said it was the first time he could remember any physical contact between them, other than occasionally squeezing past each other in the hallway. Mark called his mother. He heard her tell Elizabeth to sit down. A few moments later, he heard Elizabeth scream. That night, the 3 surviving Everetts slept together in the parents' bed. They were concerned it would be too much for Nancy to handle sleeping alone in the room she had shared with her husband. But, Mark wrote, you could never really tell how anyone was handling anything in this house. Nancy came back from the morgue with a small bag containing Hugh's wallet, watch, and wedding ring. Hugh Everett had told his wife that he wanted his ashes thrown in the trash. He was a devout atheist. He had no interest in ceremony, remembrance, or the preservation of remains. If his theory was correct, he was not dead. He had simply branched. His consciousness continued somewhere else, in another state of the wave function, experiencing another version of events. The body was debris. Nancy kept the ashes in an urn. She could not bring herself to comply with the request. 14 years later, in 1996, Elizabeth Everett took her own life. She was 39. She had been hospitalized repeatedly for mental illness. She had undergone extensive electroconvulsive therapy. She had attempted to end her life multiple times before. The 9th attempt succeeded. She left a note. In it, she asked that her ashes be thrown in the trash, like her father's. She wrote that she wanted to end up in the correct parallel universe to meet up with Daddy. That note is preserved. It is one of the most heartbreaking documents in the history of science. A woman who had suffered enormously, who had lived with a father who could not connect, and a theory that promised connection beyond death, using the language of quantum mechanics to frame the ending of her life as a reunion. 2 years later, in 1998, on what would have been Hugh Everett's 68th birthday, Nancy Everett died of lung cancer. Almost certainly, it was caused by decades of second-hand smoke from her husband's 3 packs a day habit. Mark was at her side. Mark Oliver Everett, the boy who had grown up with a ghost for a father, was now the only surviving member of his family. He channeled it into music. The Eels album Electro-Shock Blues, released in 1998, was written in response to his sister's death and his mother's terminal illness. The title refers to Elizabeth's electroconvulsive therapy. The opening track, Elizabeth on the Bathroom Floor, is composed from lines of Elizabeth's own diary. Another track, Baby Genius, is about Hugh. The album is a monument of grief, rendered in song by a man who understood quantum mechanics through the wreckage it left in his family. Years later, Mark made the BBC documentary Parallel Worlds, Parallel Lives. In it, he explored his father's work for the first time. He visited Princeton. He met physicists. He learned, slowly and with visible emotion, that his distant, impossible father had changed the way human beings understand reality. Mark said something in the documentary that stayed with people. He said he thought about how angry he was that his father did not take better care of himself, how he never went to a doctor, let himself become grossly overweight, smoked 3 packs a day, drank like a fish, and never exercised. But then he thought about how his father had said, days before dying, that he had lived a good life and that he was satisfied. Mark realized that there was a certain value in his father's way of life. He ate, smoked, and drank as he pleased, and one day he just suddenly and quickly died. Given some of the other choices Mark had witnessed, it turned out that enjoying yourself and then dying quickly was not such a hard way to go. The man who invented many worlds died in one. The man who proved that every outcome is real experienced only one outcome. The man whose mathematics guarantees the survival of consciousness in some branch was found cold and still in his bed by the son he had never embraced. And the theory lived on without him, growing, spreading, conquering, slowly, the very physics establishment that had tried to bury it. But to understand why it conquered, you have to understand the experiment that started it all, not the quantum suicide thought experiment. Something older, something simpler, something that has been terrifying physicists for over 200 years. Chapter 7. The experiment you cannot cheat. Imagine a wall with 2 narrow slits cut into it. Behind the wall is a screen. In front of the wall is a source of light. simple equipment, something you could build in a garage. And it contains, according to Richard Feynman, the central mystery of quantum mechanics. Every paradox, every impossibility, every question that has kept physicists awake for a century is packed into this one experiment. The double-slit experiment. It was first performed in 1801 by the British polymath Thomas Young. Young wanted to settle a debate that had consumed physics for over a century. Is light made of particles, as Isaac Newton believed, or is light a wave, as Christian Huygens argued? Young's setup was elegant. He directed a beam of coherent light at a barrier with two parallel slits. The light passed through both slits and hit a screen on the other side. If light were made of particles, tiny bullets flying in straight lines, you would expect to see two bright bands on the screen, one behind each slit, two strips of light corresponding to the two openings. That is not what happened. What appeared on the screen was an interference pattern, alternating bands of brightness and darkness spreading across the screen in a complex, regular arrangement. This is the signature of wave behavior. When two waves meet, their peaks and troughs interact. Where two peaks align, the waves reinforce each other and the light is brighter. Where a peak meets a trough, they cancel each other out and the light disappears. The result is a pattern of fringes, bright and dark, that only waves can produce. Young had his answer. Light is a wave. The physics community eventually accepted this conclusion, and for most of the 19th century, the wave theory of light reigned. Then came the 20th century, and everything fell apart. In 1905, Albert Einstein published a paper explaining the photoelectric effect, the phenomenon in which light striking a metal surface ejects electrons. The behavior of these ejected electrons could not be explained by the wave theory. The energy of the electrons did not depend on the intensity of the light, as wave theory predicted. It depended on the frequency. and dead in another. The observer who opens the box splits into two observers, one who sees a living cat and one who sees a dead cat. Both are real, both continue. Neither knows about the other. The double-slit experiment, under many worlds, tells a similar story. The photon goes through both slits because both outcomes are real. The interference pattern appears because the two branches interact at the quantum level before decoherence separates them. When you place a detector at one slit, the interaction between the photon and the detector causes decoherence, the process by which quantum superpositions become entangled with the environment and lose their coherent relationship. The branches separate. The interference pattern vanishes, not because observation creates reality, because observation, which is just physical interaction, triggers decoherence, which separates the branches. This is cleaner than Copenhagen. No arbitrary line between quantum and classical, no mysterious collapse, no special role for consciousness. Just the Schrödinger equation, operating continuously, splitting the world into branches whenever quantum events occur. And this is why many worlds has gained so much ground in the decades since Everett proposed it, not because it is intuitive. It is spectacularly unintuitive. An infinity of parallel universes is not an easy thing to accept, but it is mathematically simpler. It requires fewer assumptions. It treats the observer as part of the system, not an exception to it. And it resolves the measurement problem, the deepest unsolved puzzle in quantum foundations, by dissolving it. There is no measurement problem if there is no collapse. There is only branching, only entanglement, only the relentless, democratic reality of every possible outcome being realized. The experiment you cannot cheat, the photon that goes through both slits, the cat that is alive and dead, the universe that splits at every quantum junction. And in every branch, a version of you, watching, listening, wondering which version is real. All of them, that is the answer. All of them are real. Chapter 8. Every version of you is real. Right now, as you listen to this, your brain is making decisions. Not just the big decisions, not just whether to keep listening or turn this off. Trillions of microscopic decisions. Neurons are firing or not firing. Synapses are releasing neurotransmitters or holding them back. Chemical gradients are shifting. Electrical impulses are propagating through networks of cells at speeds measured in milliseconds. Each of these events, at its most fundamental level, is governed by quantum mechanics. The release of a neurotransmitter molecule from a synaptic vesicle involves the behavior of individual ions passing through protein channels in cell membranes. These ions are quantum objects. Their behavior is probabilistic. Whether a particular calcium ion triggers the release of a particular vesicle at a particular synapse at a particular moment is not strictly determined by classical physics. It is subject to quantum uncertainty. Now, this does not mean that your brain is a quantum computer, at least not in the way that term is usually understood. The brain operates at a temperature and scale where quantum coherence is quickly lost to the environment. Decoherence happens fast. The quantum randomness is real, but it is washed out by the thermal noise of billions of molecules interacting chaotically. But, under the many worlds interpretation, even washed out quantum randomness matters. Because every quantum event, no matter how small, no matter how quickly it decoheres, produces a branching. In one branch, the ion crosses the channel. In another, it does not. In one branch, the neurotransmitter is released. In another, it is held back. In one branch, a particular neuron fires. In another, it stays quiet. And each of these branchings produces a slightly different version of your brain state, a slightly different thought, a slightly different feeling, a slightly different decision. The number of quantum events occurring in your brain at any given second is staggering. There are roughly 86 billion neurons in the human brain. Each neuron forms thousands of synaptic connections. Each connection involves the movement of ions, the release of molecules, the propagation of signals, all of it riding on a foundation of quantum mechanics. The result is that the number of branches created by your brain alone in a single second is a number so large that writing it out would require more digits than there are atoms in the observable universe. And it is not just your brain. It is every brain, every cell, every molecule, every atom, every photon, bouncing off every surface, every radioactive decay, every interaction between every particle in the entire cosmos. All of it branching, all of it splitting, all of it real. The total number of branches in the universal wave function is not merely large. It is a kind of infinity that mathematicians call uncountably infinite. You cannot list them, you cannot number them, you cannot place them in sequence. They proliferate faster than any finite process can track. And in each branch, there is a version of you. This is the implication that most people find either exhilarating or horrifying, and sometimes both. In some branches, you chose differently. The job you did not take, you took. The person you did not call, you called. The risk you avoided, you embraced. Every fork in your life, every moment of hesitation, every decision that felt like it could go either way, did go both ways. Both versions exist. Both versions continued. Both versions believe they are you. But it goes deeper than life choices. Because the branching is not driven by decisions, it is driven by quantum events. And quantum events are everywhere, all the time, at every scale. The decision to turn left or right is built on a scaffold of neural activity that is built on a scaffold of molecular interactions that are built on a scaffold of quantum mechanics. The choice is real, but the branches happen whether you are choosing or not. You do not need to be at a crossroads for the universe to split. The universe splits when a photon hits a mirror, when a radioactive atom decays, when an electron tunnels through a barrier. These events have nothing to do with human choice or human awareness. They happen in empty space, in dead stars, in the cores of planets where no observer has ever existed or ever will. The branching is universal, constant, and indifferent to whether anyone is watching. This creates a profound question about identity. If there are uncountably many versions of you, which one is really you? The intuitive answer is this one. The one listening right now. The one having this experience. The one whose memories form a continuous narrative from childhood to this moment. This is you. The others are copies, variations, alternatives. But the many worlds interpretation does not support this intuition. There is no master branch, no preferred version, no original from which the copies descend. Every version has an equally valid claim to being you. Every version has continuous memories. Every version believes it is the real one. The only difference between you and your nearest quantum neighbor is that in their branch, one photon bounced off your retina instead of being absorbed, or one neuron fired 1 millisecond earlier, or one calcium ion went left instead of right. You are not a single person. You are a vast ensemble of persons, diverging from each other at every quantum tick, each carrying a slightly different version of your experience, your thoughts, your identity. And here is where free will becomes complicated. In a universe where every possible outcome of every quantum event is realized, what does it mean to choose? If you are deciding whether to quit your job, and in one branch you do and in another you do not, then both decisions are made, both paths are taken. You did not choose one over the other, you chose both. Or rather, one version of you chose one, and another version chose the other, and the choice was determined, at the most fundamental level, by quantum events in your neural circuitry that branched the universe before you even finished formulating the thought. This feels like freedom has been abolished. If every decision is made in some branch, then no decision is really a decision. You are not selecting from possibilities. You are simply existing at the point where possibilities diverge. But there is another way to look at it. In many worlds, you are never trapped by a single outcome. Every mistake is a path taken only in this branch. In other branches, you chose differently. In other branches, the worst thing that ever happened to you did not happen. In other branches, the opportunity you missed was seized. There is a strange liberation in this. Not because you can access those branches, you cannot, but because the mathematical structure of reality contains all possibilities. Nothing is lost, nothing is wasted. Every version of your story is told. The physicist David Deutsch, who has thought more carefully about many worlds than almost anyone alive, has argued that many worlds actually rescues free will in a counterintuitive way. Under determinism, the traditional rival to free will, the future is fixed. You could not have done otherwise, but under many worlds, you do otherwise. In another branch, you took the other path. The structure of reality accommodates all your possible choices, and each version of you experiences the consequences of one of them. Free will, in this framework, is not the ability to choose one outcome from many. It is the fact that all outcomes are chosen by all versions of you simultaneously. Whether this counts as free will or its elimination depends on what you mean by you. If you are a single thread of consciousness, a single narrative running through time, then many worlds obliterates free will. Your choices are not choices, they are branches. If you are an ensemble, a family of selves diverging from a common origin, then every choice is made, every path is explored, and freedom is not an illusion, but a structure woven into the fabric of quantum mechanics itself. Now consider what this means over a lifetime. You are born. In every branch, you are born, because the branches that led to your existence converge at that point. But from that moment on, the divergence begins. By the time you are a year old, the number of branches in which you exist has become unimaginably large. By the time you are 10, the number defies any human analogy. By the time you are 30, the number of versions of you that exist across the universal wave function is a quantity that has no name in any language. And each of these versions believes it is the original. Each has memories. Each has a personality. Each has a life story that it considers singular and meaningful. None of them is wrong. All of them are you. And none of them knows about the others. By the time you reach old age, something strange has happened. The vast majority of branches in which you once existed have seen your death. Heart attacks, cancers, accidents, diseases. All the mechanisms that end human life have ended it in almost every branch. The number of surviving versions dwindles. The ensemble thins. The probability of your continued existence, weighted across all branches, approaches zero. But it does not reach zero. In some extraordinarily improbable branch, you survive. You are an extreme statistical outlier. You are the version of yourself that has beaten every odd, dodged every threat, outlasted every mechanism that should have ended you. You do not know you are an outlier because you have no access to the branches where you died. You simply continue. And you do not know it. That is the strangest part. You walk through your life, aging normally, experiencing the usual sequence of events, with no awareness that from the perspective of the universal wave function, your continued existence is vanishingly unlikely. You feel normal. You feel ordinary. You feel like the same person you have always been. But you are not ordinary. You are the survivor of a cosmic lottery that has been running since the moment you were born, culling branches at every quantum tick, and you are the one who is still here, not by luck, not by destiny, by the relentless branching of a wave function that produces every outcome and filters your experience to the branches where you continue. Every version of you is real. You just happen to be this one. Chapter 9. The Math That Broke Reality. There is a number so large that if you tried to write it out, you would run out of atoms in the universe before you ran out of digits. It is not a theoretical abstraction. It is the number of branches in the universal wave function that have diverged from the state of reality that existed 1 second ago. We are used to big numbers. Astronomers deal in billions. Chemists work with Avogadro's number, roughly 6.02 times 10 to the 23rd power, the number of molecules in a mole of a substance. Computer scientists count in petabytes and exabytes. The numbers that emerge from the many worlds interpretation make all of these look like pocket change. To understand why quantum immortality is not just a philosophical curiosity but a mathematical implication, you need to understand how probability works in infinite systems. And that understanding begins with a concept that sounds simple but leads somewhere very uncomfortable. Given enough tries, any event with a non-zero probability will occur. This is a standard result in probability theory. If you flip a coin, the odds of getting heads 100 times in a row are roughly 1 in 10 to the 30th power. That is a 1, followed by 30 zeros. It will almost certainly never happen in the observable universe as we experience it. But in the many worlds interpretation, it does happen, because every outcome occurs. Every flip produces a branch where it landed heads and a branch where it landed tails. After 100 flips, there are 2 to the 100th power branches, which is approximately 1.27 times 10 to the 30th power. And in one of those branches, every single flip came up heads. In one branch, you flipped heads 100 times in a row. In another, you flipped tails 100 times in a row. In most branches, you got a mix. But the extremes exist. The extremes are real. They are as physically real as the most probable branches. They carry observers. They carry consequences. Now replace the coin with your survival. At every moment, quantum events in your body could go one way or another. A DNA repair enzyme catches a mutation or does not. An immune cell identifies a cancerous cell or misses it. A blood clot forms or dissolves. Each of these events has a probability. Most of the time, the probability favors your continued health. But occasionally, rarely, the probability goes the other way. Under normal, single-world physics, these rare events accumulate. Over a lifetime, enough go wrong that the body fails and you die. This is aging. This is mortality. This is the human condition. Under many worlds, every outcome happens. In most branches, the rare bad events occur and you die on schedule. But in some branches, every single quantum event that could have harmed you happened to go the other way. The mutation was repaired. The cancer cell was caught. The clot dissolved. The aneurysm held. In those branches, you survive far longer than any statistical model would predict. And the logic of conscious experience, the fact that you can only observe a branch in which you are alive, means that from your first-person perspective, you always find yourself in a surviving branch. You never experience the branches where you died because there is no you there to experience anything. This is the mathematical foundation of quantum immortality. It is not a hypothesis that needs experimental confirmation. It is a logical consequence of 3 premises. 1. The many worlds interpretation is correct. 2. Consciousness requires a functioning physical substrate. 3. Every quantum event produces a branching. If all 3 are true, quantum immortality follows as inevitably as 2 + 2 = 4. The question, of course, is whether all 3 premises are true. The first premise, whether many worlds is correct, is the subject of the deepest ongoing debate in the foundations of physics. When Everett proposed his theory in 1957, it was ignored by almost everyone. By the 1970s, Bryce DeWitt's advocacy had brought it to wider attention. By the 1980s, a small but growing community of physicists took it seriously. By the 21st century, It had become one of the mainstream interpretations of quantum mechanics, supported by some of the most prominent physicists in the world. David Deutsch, a professor at the University of Oxford and one of the founders of quantum computing, is a committed advocate of many worlds. He argues that quantum computation itself provides evidence for the interpretation. A quantum computer performs calculations that would take a classical computer longer than the age of the universe. Where are those calculations happening? Deutsch argues they are happening in parallel branches of the wave function. The computational power of a quantum computer is, in effect, borrowed from its counterparts in other universes. Sean Carroll, a physicist at Johns Hopkins University and a prolific writer on quantum foundations, has also championed many worlds. Carroll argues that many worlds is the most parsimonious interpretation because it adds nothing to the mathematics. The Schrödinger equation, the fundamental equation of quantum mechanics, already contains branching. The Copenhagen interpretation adds something extra, the collapse postulate, which is not in the equation. Many worlds takes the equation at face value. It is not adding complexity, it is removing it. Max Tegmark, who we have already met as the architect of the quantum suicide thought experiment, is another advocate. Tegmark has argued that the multiverse predicted by many worlds is not hypothetical but mathematical. If the equations of physics describe reality and the equations describe branching, then the branches are real. Surveys of physicists' preferred interpretations vary widely, but the trend over the past 2 decades has been unmistakable. Many worlds has grown from a fringe idea to a serious contender. In some polls, particularly among quantum computing researchers and cosmologists, it is the most popular interpretation. In others, Copenhagen still holds a narrow lead, but the margin is shrinking. The second premise, that consciousness requires a functioning physical substrate, is less controversial in physics but deeply debated in philosophy. Most neuroscientists and physicists accept that consciousness emerges from physical processes in the brain. No brain, no consciousness. This is the standard materialist view. If this is correct, then consciousness cannot exist in a branch where the brain has been destroyed. The branching of the wave function does not carry a disembodied soul to a new branch. It simply means that in branches where the brain functions, consciousness exists, and in branches where it does not, consciousness does not. The third premise, that every quantum event produces a branching, is a direct consequence of the Schrödinger equation applied universally. If the wave function never collapses, then every interaction that produces a superposition produces a branching. This is not controversial within the many worlds framework. It is the definition of the framework. So the debate reduces to the first premise: is many worlds correct? And here is the uncomfortable truth. No one has produced a definitive refutation. There have been objections, serious ones. The most important is the preferred basis problem. When the universe branches, what determines the branches? The Schrödinger equation does not specify a unique way to decompose the wave function into branches. Different decompositions give different sets of parallel worlds. Why should one be preferred over another? The standard response involves decoherence. When a quantum system interacts with its environment, information about its state leaks into the surrounding particles. This process, called quantum decoherence, effectively selects a preferred set of states, the pointer states, which are the only states robust enough to survive the constant bombardment of environmental interactions. The branches that emerge are not arbitrary. They are determined by the physical dynamics of decoherence. The theory of decoherence was developed in the 1970s and 80s by H. Dieter Zer, Wojciech, Zurek, and others. It was not developed as a defense of many worlds, but it turned out to provide exactly the mechanism that many worlds needed. The branches are real. They are selected by physics, not by convention. And they are the reason the classical world looks classical, even though the underlying physics is quantum. Another objection concerns probability. In many worlds, every outcome occurs. So what does it mean to say that one outcome is more probable than another? If both happen, how can one be more likely? This is the Born rule problem. Max Born's rule, proposed in 1926, says that the probability of a particular measurement outcome is given by the square of the amplitude of the corresponding term in the wave function. This rule is experimentally confirmed to extraordinary precision. But in many worlds, where all outcomes are realized, deriving the Born rule from the structure of the theory has proved challenging. Several derivations have been proposed. Deutsch offered a decision-theoretic argument in 1999. David Wallace refined it in subsequent years. Their argument runs roughly as follows. A rational agent in a branching universe, one who assigns weights to future branches in a self-consistent way, is forced by the axioms of rational decision-making to assign weights that match the Born rule. The probabilities are not frequencies. They are rational credences. They tell you not what will happen, because everything will happen, but how to distribute your expectations across the branches. Not everyone is convinced. The debate is ongoing, but the trajectory is clear. Many worlds has gone from a laughable idea dismissed by Niels Bohr's inner circle to one of the leading interpretations of quantum mechanics, supported by some of the most distinguished physicists of the 21st century. Hugh Everett did not live to see this vindication. He died in 1982, believing in his theory, drinking himself to death, surrounded by a family that could not reach him. By the time many worlds achieved mainstream respectability, Everett had been dead for decades. But the math survived. The math always survives. The personalities fade, the politics dissolve. The social pressures that silenced a brilliant young man in the 1950s have evaporated. What remains is the Schrödinger equation, unchanged since 1926. And the question that Everett asked, what if it is telling the truth? What if the wave function never collapses? What if every possible outcome is real? What if you have already died, in more branches than you can imagine, and the reason you are still here is not luck, but law? The math does not flinch. The math does not care about your comfort. The math says what it says. And what it says is that every version of every event is happening right now, in an infinity of branches, spreading outward from this moment like the surface of an expanding sphere. And you are riding one thread of that expansion, the thread where you survived, the thread where you are listening, the thread where you are still asking questions. But there is one more question, the final one, the one that cannot be answered by mathematics or experiments or thought experiments. What happens at the end? Not the end of your life, the end of your experience, the moment when consciousness fades to nothing, if it ever does. What is that like? What does quantum mechanics say about the boundary between being and not being? That is where we go next. Chapter 10. What happens when you close your eyes? You have been alive for your entire life. That sounds obvious. It sounds trivial, but it is the most important fact about your existence, and it is the fact that quantum mechanics cannot fully explain. You have never experienced unconsciousness. Not really. You have fallen asleep and woken up, but the gap between those events is not an experience, it is an absence. You did not notice the hours passing while you slept because there was no one there to notice. You closed your eyes and opened them, and the clock had moved forward. The you that fell asleep and the you that woke up feel continuous, but the continuity is an inference, not an observation. You have never experienced anesthesia from the inside. You count backward from 10, and then you are in the recovery room, and the operation is over. The gap is not darkness. It is not silence. It is nothing. Not the experience of nothing, but the absence of experience entirely. These gaps in consciousness raise a question that physics has not answered. What is consciousness? What generates it? What sustains it? And what exactly happens to it when it ends is less than #0. 5# is greater than. Quantum mechanics does not address consciousness directly. The Schrödinger equation describes the evolution of quantum states. It does not contain a variable for awareness. There is no operator in the mathematical formalism that corresponds to the subjective experience of being. And yet consciousness is the only lens through which any of this matters. Without consciousness, the wave function branches, and nobody notices. Without consciousness, the double-slit experiment produces patterns that no one interprets. Without consciousness, quantum immortality is a mathematical curiosity with no observer to experience it. So what does quantum mechanics, combined with our best understanding of consciousness, say about what happens when you close your eyes for the last time? There are 4 possibilities. The first possibility is the Copenhagen answer. Death is death. The wave function collapses. The system that was your brain ceases to function. Consciousness, which was a product of that system, ends. There is no continuation, no branching, no survival in another universe. The mathematical description of you reduces to a classical state, a body without awareness, and that is the end of the story. Under this interpretation, quantum immortality is fiction, a mistake, an overreading of equations that were never meant to describe the fate of conscious beings. The wave function collapse happens at the moment of measurement, and the measurement that is your death produces exactly one outcome: non-existence. This is the most commonly taught view. It is the view that most physics textbooks imply. It is clean, stark, and final. It also requires the collapse postulate, which is, as we have discussed, a rule added to the mathematics from outside, with no physical mechanism to explain it. The second possibility is many worlds without immortality. The wave function never collapses. Branching is real. But consciousness is tied to the physical state of the brain. And when the brain degrades, consciousness degrades with it. There is no magical transfer to a surviving branch. The version that Everett may have privately believed, the version that inspired his daughter's final note, the version that is either the most liberating idea in the history of human thought or the most terrifying. Under full quantum immortality, death is not an event you experience. It is an event that happens to your body in branches where your consciousness is no longer present. The consciousness itself continues, riding the narrowing channel of surviving branches, experiencing an increasingly improbable existence, aging and fading but never reaching zero. The problem with this version, as we discussed, is the fading. Even its advocates acknowledge that surviving branches become thinner and thinner. The quality of consciousness in those branches degrades. The experience of being alive in the most improbable surviving branch may bear little resemblance to the experience of being alive in a healthy, typical one. Immortality, if it exists, is not a gift. It is a slow dissolve. The fourth possibility is something beyond physics entirely. Perhaps consciousness is not fully described by quantum mechanics. Perhaps it is not fully described by any physical theory. Perhaps there is something about the subjective experience of being, the redness of red, the painfulness of pain, the sheer fact that there is something it is like to be you, that escapes the Schrödinger equation as completely as it escapes classical mechanics. This is the hard problem of consciousness, named by philosopher David Chalmers in 1995. Why does subjective experience exist at all? Physics can describe the behavior of every particle in your brain without ever mentioning consciousness. The equations work perfectly without it, and yet it is there. You are there. Awareness is there. If consciousness is not fully captured by physics, then physics cannot tell you what happens to it at death. The wave function branches. The brain stops. But what happens to the awareness, the subjective thread, the first-person experience, is simply not in the jurisdiction of the Schrödinger equation. It is an open question, and it may remain open. Under this view, quantum immortality is not true or false. It is simply not the right framework. The question of what happens after death is not a question about wave functions or branching or probability amplitudes. It is a question about the nature of mind, and mind may be something that physics, in its current form, is not equipped to answer. So where does this leave us? We have traveled a long road tonight. We started with the mundane reality of your morning commute and the cosmic rays passing through your body. We met the impossible survivors, the people who beat odds so extreme that probability theory buckles under the weight. We sat in front of the quantum gun and watched the universe split with every pull of the trigger. We followed Hugh Everett III from a lonely childhood in Washington, D.C., to a night of sherry and revolutionary equations at Princeton. We watched him challenge the most powerful physicist in the world and lose. We watched him retreat into the Pentagon, into defense contracts, into a life of cigarettes and gin and mathematical solitude. We watched his theory rise from the dead while he drank himself into an early grave. We stood in the ruins of his family. Elizabeth's note, Nancy's cancer, Mark's music, the ashes that were and were not thrown away. We passed through the double slit experiment, the gateway to quantum strangeness, and saw a photon go through two doors at once. We explored the branching, the uncountable infinity of worlds that split from this moment in every direction. We looked at the mathematics, the Born rule, decoherence, the Schrödinger equation that runs like a river through everything that exists. And we arrived here, at the edge, at the boundary between what physics can say and what it cannot. The truth is, no one knows what happens when you close your eyes for the last time. Not physicists, not philosophers, not neuroscientists, not the man who wrote the equations that opened this question in the first place. The Copenhagen interpretation says the story ends. Many worlds says the story branches. Quantum immortality says the story continues. The hard problem of consciousness says we do not understand the narrator well enough to know. Here is what we do know. You are here, right now, conscious, aware, asking questions. That is not trivial in a universe that is mostly empty space, mostly dead matter, mostly cold vacuum stretching for billions of light years in every direction. You are a knot of organized complexity that can think about itself. You can contemplate your own existence. You can wonder about your own death. You can hold in your mind the mathematical structure of a theory that says you might live forever and simultaneously doubt its conclusions. That capacity, that awareness, that impossible, unexplained miracle of being a conscious entity in a physical universe may be the only immortality that matters. Not the immortality of surviving in every branch. Not the immortality of quantum selection effects rooting your consciousness around death. Not the immortality promised by religions or hoped for by billionaires or implied by equations. the immortality of having been here at all. Hugh Everett III was born in 1930 and died in 1982. 51 years. A blink by cosmic standards. He wrote equations that changed how human beings understand the structure of reality. He proposed that every possible version of events is real, that the universe is vaster than anything previously imagined, that consciousness threads its way through an infinity of branches like a needle through infinite fabric. He believed, perhaps, that he would survive his own death, that his consciousness would continue in another branch, that the trash can was not an ending but a formality. His daughter believed it too, and she tested it. Whether they were right is a question that can only be answered by one person at a time. The experiment is available to all of us. It comes free with consciousness, and it produces a result that the experimenter can never share. In the meantime, we have this moment, this branch, this version of events in which you are alive and listening and thinking and wondering. Maybe it is the only branch. Maybe it is one of uncountably many. Maybe the difference does not matter. What matters is that you are here, that the universe produced something that can ask whether the universe has produced it before, in other places, in other branches, in other versions of tonight. And that question, the question of whether consciousness has a special place in the physics of reality, is the deepest question physics has ever encountered. Deeper than relativity, deeper than quantum mechanics, deeper than the origin of the universe itself. Because without consciousness, there is no one to ask the questions. And without the questions, physics is just numbers in an empty room. Hugh Everett's mathematics is beautiful. His life was tragic. His theory may be correct. His family was destroyed. And the universe keeps branching, indifferent to all of it, splitting and splitting and splitting into a future that contains every possibility, including the possibility that none of this matters, and the possibility that it is the most important thing that has ever been thought. Both are real. That was his point. If you enjoyed this journey, please like this video and subscribe to the channel. Tell me in the comments what topic you would like to explore next. Whether it is the nature of time, the mysteries of dark energy, the physics of black holes, or something else entirely, your suggestions shape where we go from here. Thank you for being here tonight. Thank you for listening. Thank you for being the version of yourself that stayed until the end. In some other branch, you turned this off hours ago, but in this one, you are still here. And that means something, even if we do not yet know what. Good night. Sleep well, and try not to think too hard about how many versions of you are closing their eyes right now.